If I start 2 feet in front of the CBR, in other words, the position at time 0 is 2, and walk away from the CBR at a constant speed of 3 feet per second, I have walked what? For 6 seconds, I've walked at 3 feet per second. So I've gone a total of what? 18 feet, haven't I? But I started at, here's the CBR, I started at 2 feet, and then I walked 18, from here to here's 18, so I'll end up at 20, right? S of 6 is 20 feet. Is that what you got? Can't just say my position is 18 feet. That would be my position if I started right at the CBR, but I started 2 feet in front of the CBR. Okay, how far did you travel in these 6 seconds? Well, that's the 18 feet. In other words, S of 6, my position at time 6 seconds is 20 feet. Need to learn how to use the eraser on this pencil. S of 6 minus S of 0 is 20 feet. My position at 6 seconds was 20 feet from the previous bullet. My position at 0 seconds was 2 feet. That was given, so the total distance is 18 feet. In other words, I traveled 3 feet per second for 6 seconds, so I've traveled 18 feet. Okay? Second bullet point. For this scenario, the one we just talked about, draw the graph of the velocity function and find the area of the region between this graph and the horizontal axis on the interval of time between 0 and 6. So, is the velocity a positive 3 or a negative 3? We know the speed is 3, but velocity, speed's absolute value of velocity. Think about it. Is the velocity positive 3 or negative 3? And how do I know? It's positive 3 because I'm walking away from the CBR. Position is increasing. So here's the graph of the velocity function. It's just f of x, or f of t, is 3, and my f is v. And I was asked for some reason to find the area of this region under the velocity curve above the horizontal axis between the vertical lines 0 and 6. Well, that's just a rectangle, and the height is 3, the width is 6, so the area is 18. So there's 18 of these square units here cover this rectangle. But let's think about the units in this practical application of velocity and time. That 3 is really what? That's a velocity. That's 3 feet per second. And this 6 is what? It's 6 seconds. So when I multiply 3 feet per second times 6 seconds, I just get 18 feet, don't I? Is it a coincidence that my answer to this question, how far did you travel in these 6 seconds, was 18 feet, was the same as the answer to this second bullet, the area under the velocity function on the time interval 0 to 6, for both of these I got 18 feet. That's not a coincidence. If you look in section 5.1, back up a little bit, there's a section on the distance problem. Page 373, the distance problem. And they end with saying, on page 375, the distance traveled is equal to the area under the graph of the velocity function. The distance traveled is the area under graph of velocity function. We observe that in this scenario, right? The area under a velocity function was 18. The distance traveled was 18. Now, what does this have to do with, what is the connection with the fundamental theorem of calculus? And by the way, let me back up. The first WebAssign problem for homework on this assignment has to do with the distance traveled, is the area under a velocity graph. Okay, what does this result have to do with the fundamental theorem of calculus? Well, we know that the derivative of position, how fast position is changing with respect to time, how fast position is changing over time. The derivative of position is velocity, right? So if the derivative of position is velocity, that tells us the antiderivative of velocity is position. And there are lots of different position functions that have the same velocity function or derivative, so I really need this plus c. In fact, go back up to what we did just a minute ago. Wouldn't this be our graph of velocity regardless of where we started, if we started at the CBR? So if S of 0 was 0, or if we started as we really did at 2, S of 0 is 2, the velocity graph would be the same, wouldn't it? Okay? Since the derivative of position is velocity, antiderivative of velocity is position. But we just learned that the distance traveled is the area under the velocity function. The area under the velocity function on a time interval a to b, the area under a velocity function on the interval on the horizontal axis, in other words, that'd be a time interval from a to b. This is the area under the velocity function. That is the total distance traveled. But what is the total distance traveled? Look back up here. Look here. What's the total distance traveled? It's S of, in our problem, 6 minus S of 0, but in general, S of B minus S of A. Okay? Now, let's compare these two things. To compute this definite integral, we can just evaluate the position at B, evaluate the position at A, and subtract. But isn't the position at B just an antiderivative of velocity? And isn't the position at A an antiderivative of velocity? Of course, evaluated at A and B. So look, putting these two together tells us that the value of the definite integral is equal to the indefinite integral evaluated at B minus the indefinite integral evaluated at A. We write that more concisely as this. But this is the fundamental theorem of calculus, right? Which says the value of a definite integral is just the value of the indefinite integral evaluated at the endpoints, and you subtract those. Now again, in section 5.3 there's a formal proof, but this can give us a glimmer of why it might be reasonable that the fundamental theorem of calculus would be true, grounded in a practical example. It's really not obvious why the limit of a sum, the area under a curve, would be related to an antiderivative. But this shows us a practical example where it is.